Hello everyone, my name is James Ryan, and today I'm here to teach you about combinatorics. So, let's get started. First of all, what is combinatorics? Well, combinatorics is a sub-branch of probability, which is a sub-branch of mathematics. Combinatorics is especially useful for problems in which a specific amount of objects, for example 3, we'll color them light blue so that they're easier to identify, need to be placed in a specific number of spaces. For example, how many different ways can we rearrange these 3 balls and put them into these 4 spaces? Well, let's find out. First of all, to make things a bit more clear, I'm also going to recolor these other balls so that we can differentiate between them. So, what's the probability of... Let's start, first of all, with the different amount of ways that this blue ball can be placed. Well, there's 4 different ways that this blue ball can be placed. So we'll start off with the number 4. So now, the blue ball will be taking up one of these spaces. So, what's left over for the red ball to occupy is only 3 spaces. So instead of timesing by 4 again, we're only going to times by 3. Then, once the red ball has occupied a space, there's only 2 possible other spaces for the green ball to go. So, we simply times by 2. Okay? Even if we had more holes, for example, 5 of them, it wouldn't make a difference because there were only... Well, actually, it would. Sorry, what I meant to say was, if we added another hole, it would make a difference. There would be a lot more different combinations, because now instead of 4 times 3 times 2, it would instead be 5 times 4 times 3. Because the first ball, the blue ball, would have had 5 different places it could go, the red ball could have had 4 different places it could go, and the green ball would have had 3 different places it could go. So, this turns out to be 5 times 4 is 20, times 3 is 60 different combinations. Now, I'm not going to show you them all, because that would take a long time. But, just note that we only put these balls here for simplicity's sake. This blue ball could have gone in any of these 5 different ways, of these 5 different spaces. The red could have gone in any of these other 5 spaces, and the green, so on, so on. So, now, we need a quick and easy way of writing stuff like this down. But not yet. One more thing. What about combinations? What if these balls were all the same color? I'm not going to paint them yet because we still want to be able to differentiate them. But if they were all blue, then we wouldn't care if this ball here was the blue one and this one was the red one. At the moment we do, because what we're looking at here is not really called the amount of combinations, but what we're actually looking at is something called a permutation. Okay? Just a bit of terminology. I'll tell you what a combination is very soon. But see, these balls have swapped positions. Now, if we were looking at permutations, we would count this as a different permutation. But if we're looking only at combinations and we don't care about that swapping, then that's what combination is. Combinations is when you only care about which spaces are occupied by the 3 balls, but not which balls occupy each space. So if these were all blue balls, then to us, all of these situations would be the same thing. Doesn't matter if these 2 balls here and here swap, because it's the same thing. So we've got this nice amount of permutations here, but now we got to divide by the amount of... You've got to divide so we can get the amount of combinations. So how do we get the amount of combinations? Well, how many different permutations can we have that give us the same amount of combinations? Well, a permutation different permutations that count as the same combination are just these three balls in the same positions, but rearranged among themselves. So it's basically as if we've got three other holes, and we're just rearranging these balls between them. So instead of this ball going here, and this ball going here, and this ball going here, it could work a little differently with this ball here going there, and this ball here going there instead. And so, because for every single permutation, there will always be the exact same amount. For every single combination, there will always be the exact same amount of permutations that all represent the same combination. We only need to divide this total amount of permutations by the amount of combinations by the amount of permutations there are per combination to get the amount of combinations there are. So we divide 5 times 4 times 3 by the amount of ways these balls can rearrange themselves. Now, what's the amount of ways these balls can rearrange themselves? Well, this first ball here has 3 different places it can go into. So we're going to write, 3. So it's got a 3, okay? Okay, but then this second ball will then only have 2 different spaces it can go to. So times 2. And then this ball here, this last ball after the third ball, has been moved into one of the spots, whichever one, will only have 1 possible place it can go to. So times 1. And there you have it. That's the amount of combinations. It's this number right here. So, the amount of ways we can arrange the amount of different permutations we have when we arrange 3 differently colored balls among 5 spaces is 5 times 4 times 3, or 60 different possible permutations. 60 different ways. If the balls are all the same color, and we only care about where the balls are placed, not which balls are placed where, or even if they are different colors, but we only care about the places, then it instead becomes 5 times 4 times 3 divided by 3 times 2 times 1. So the 3's cancel out, and it becomes 5 times 4 divided by 2, or 20 divided by 2, which equals 10. So there's only 10 different ways, and I could show you these 10 ways, but you should try it out yourself, or just take my word for it, whichever suits you. Now, sometimes you'll get a problem where instead of having where you'll have more objects than holes. So let's take a look at that. Okay? So, say you have 5 objects, but you only have 3 holes. As you can see, this is the reverse situation of what we had before. Well, let's see how this can work. Well, we could try and put the objects in the holes. So we would say, well, how many different ways can this first object go in? Well, there's 3 different ways it can go in. So if we just times by 3, we'd get 3 different ways, and then the next ball will have 2 different ways, and then the last ball will have 1 different way. But there's a problem with this. It doesn't take into account that we could have started with a different ball. So let's try that again. One thing to realize is that when you are placing these objects, as in the previous example, just by putting the objects in different spaces, it's like you're assigning the object to a space. So what we can do instead now is, instead of assigning objects directly to spaces, we can assign spaces to objects. And when you're assigning spaces to objects, it becomes the same problem we just had. How many different objects can this first space be assigned to? 5. And this second object? 4. This third object? 3. And that's it. No more spaces to assign objects to. No more spaces to assign objects to. So you've got 5 times 4 times 3. And Now, to get the amount of combinations instead of permutations, you simply have to divide by the amount of ways that the three spaces can be rearranged among themselves. So that's just 3 times 2 times 1, or 6. So just divide by 6, and you have the same answer as before, 10. So these problems, the problems of assigning of how many different ways you can put 5 objects into 3 spaces, and how many different ways you can put 3 objects into 5 spaces, are exactly the same problem. In other words, they are what mathematicians call isomorphic. So, now what? What do we do now? How can we make this into an easily solvable equation? Something that you could give to a machine. Something you don't. And what if you had ridiculous numbers? How would you do it? You can't just type in 5 times 4 times 3. You can't just type in a million times 999,999 times 9,999,000. Whatever. You can't just keep typing all the numbers into your calculator. That would take ages. What if you had, how many different ways can a million objects go into a billion spaces? That would be ridiculous, So, luckily, mathematicians have devised a notation. I'm going to introduce you to something called the factorial. Now, when you see a number n in front of an exclamation mark, we call that n factorial. And n factorial means that you get the number, you start off with the number n, you start off with that number, n, and n is whatever number you choose, but it has to be an integer, so it has to be, a whole number, and it has to be positive, or 0. It can be a positive integer or 0, but it can't be negative. So, when you see n exclamation mark or n factorial, what it means is you get n, and then you times it by n minus 1, or the number, or the integer underneath n, the next lowest number. Then you times it by n minus 2, and so on, and until you get to 1. Then you times it by 1. Okay? So, for example, if I had, say, 4 factorial, it means 4 times 3 times 2 times 1. Okay? However, if I had 6 factorial, it would then be 6 times 5. Yeah, it would be 6 times 5, then times 4, times 3, times 2, times 1. So how is this useful to us? Well, as you saw before, what we had was, we had 5 times 4, and then times 3, and then we stopped. Okay? So how can we represent this with factorial notation? Well, what we would do is we would write 5 factorial, alright? And then we would divide 5 factorial by 2 factorial. And here's why. If you remember, 5 factorial means 5 times 4 times 3 times 2 times 1. While 2 factorial means times 2 times 1. So it's just 2 and 1. So then, if we have these numbers, the 1's cancel out, not that they did anything anyway, but then the 2's cancel out as well, and you're left with just 5 times 4 times 3. So in general, if you just want to times all the numbers from a particular number to a particular other number, say from 5 to 3, you just do that number factorial. So here I've got 5 factorial, and then you do that other number minus 1, 2 factorial. Okay? So how does this relate to what we've already done earlier? Well, earlier we posed the following problem, but now we're going to generalize it. So say you have a particular number of objects. We'll call that number n. Okay? So you have a particular amount of objects. and we're going to call this amount of objects n. Now the thing about these objects is we want to place them in a set of spaces, and we'll define the number of spaces we're trying to put these n amount of objects into as k. So we've got n amount of objects that we're trying to put into k different holes, and we want to know how many different ways we can do so. How many different ways can you get n amount of objects into k different holes? So first of all, let's find out how many different ways this first object can go into k different holes. So this first object, how many different ways? So there are k different holes it can go into. So it can go k times. Then how many different ways can this next object go? Well, it can go k minus 1 times. So times k minus 1. And hang on, I can't do brackets, so just assume these are like really badly drawn brackets, okay? And then how many times can this next ball go in? Well, that goes k minus 2 times. And this keeps on going until all of these balls here are done. And the last of these balls will be, well, as you can see, the first ball went in k times, but the second ball went in k minus 1 times. So was the second ball goes minus 1 times. So if you minus 1, and that's how much you minus from k. So if it was the 100th ball, would go in k minus 99 times. Okay? So the nth ball, because when you get through all these balls, you're going to have n amount of balls, and we're assuming there's less balls than that n is less than k, or there's less balls or objects that we need to put than holes that they need to be put into. So when we get to the nth object, it'll go in k minus n minus 1 times. So k minus, in brackets, n minus 1. Now, because we're doing minus something in brackets n minus 1, it actually becomes k minus n plus 1. So if we get rid of these brackets, the amount of times the last or nth ball can go in is k minus n plus 1. Now, so we've got to go from k to k times k minus 1, and so on, and so on, and so on, until we get to times this thing, k minus n plus 1. Okay? Now, didn't I already tell you a neat trick for what we would do, how we can use factorials to easily express that we want to times a bunch of numbers from one number to another? Okay? So first of all we start with the biggest number we want to keep timesing by. So we start off with k factorial, because we want to start off with k factorial, and then we'll start heading towards a lower number. So we'll go k times k minus 1 times k minus 2, so on, so on. And then we need to stop when we get to the k minus n plus 1. So to do so, we simply need to divide by that lower number minus 1. So what's k minus n plus 1 minus 1? Well, it's just k minus n. So what we've got here is k minus n factorial. So k minus n factorial. Now, I've actually swapped around these letters a bit, but I'll rectify that at the end. So we've got k divided by k minus n factorial. And this, right here, is the amount of ways n objects can go into k spaces. Okay? So, how many different ways? Let's see if this works with our old formula. Remember our old tried and true. How many different ways can 5 balls go into how many different ways can 3 balls go into 5 spaces? Well, let's find out, eh? So 3 balls means that n is 3, and k spaces means that k is 5, because there's 5 spaces and 3 balls. So we got 5 factorial, which is 5 times 4 times 3 times 2 times 1. So 5 times 4 is 20, times 3 is 60, times 2 is 120. So we've got 120 on the top. So this k here, this k exclamation mark is 120. Okay, I'll just write that down. 120. So because we've got 5 spaces, and then we divide by k minus n factorial. So k is 5, n is 3, so we divide by 2 factorial. And what's 2 factorial? Well, 2 factorial is just 2 times 1, which is just 2. So this entire thing equals 60. So that works so far with the amount of permutations. But what about the amount of combinations? Well, it's actually quite simple. Remember, we already have this, and to get the amount of combinations from the number of permutations, you just divide by the amount of different ways the amount of objects can rearrange themselves. So we've currently got n objects. So now we want to know how many different ways can n objects rearrange themselves. Well, we've already got this formula here, and we'll just plug n into it. So if we'll just make k equal to n, and we'll make this n also equal to n. So let me just copy and paste this over here. Okay? So if we make it like so, we now have, if we've just got the same amount of objects as wholes, the formula becomes a bit simplified. It becomes n factorial divided by n minus n factorial. N minus n factorial. But what is n minus n factorial? Well, n minus n factorial is just 0 factorial. Now, I know what you're thinking. 0 factorial. Well, what is that? Well, 0 factorial is defined as 1. So, 2 factorial is defined as 2. 1 factorial is 1 times 1, so that's defined as 1. But 0 factorial is also defined as 1. So this is just n factorial divided by 1, or simply just n factorial. That's right. So just n factorial. So if we want to divide this amount of permutations here by the amount of ways the n objects can rearrange themselves, so we can get the amount of combinations, we just have to divide by n factorial. And notice how this is the bigger division sign. So we got k, then we're dividing k by k minus n factorial, and then we're dividing by n factorial. So we don't even need this underline. We can just stick the n factorial right here. And there we have it. The amount of combinations is k factorial divided by k minus n factorial, n factorial. Now, what if you have a... Now we'll answer the other question. What if k and n are swapped? So I'm just going to clean up a little here. Just clean this up. Chop off a little bit of that ball. Doesn't matter. What if n and k are swapped? What if the bigger number of objects, whether the bigger amount of stuff, whether it be wholes or objects, becomes n and the smaller k? Well, then you just swap the letters around. You just put n in the top instead of... You just replace all instances here of k with n, and all instances of n with k. So instead of k factorial become k minus n factorial becomes the other way around. It becomes n factorial divided by n minus k factorial, k factorial. Okay? And actually that's the way it's normally done. I just messed up here with what I called the objects and what I called the spaces. I just thought I would call n objects because that seemed natural to me, but I guess that's not what it's actually done. Now, there is another way of doing these things. What we call another easy way of saying k factorial over k minus n factorial. Well, actually, I'm going to rewrite it now as what it's properly called, which is actually n factorial over n minus k factorial. Don't worry, it doesn't make a difference. I've just changed the lettering around. We can represent this easy sum as something called, we can just call it n choose k, And the way you do... No, you don't do that. You call it N, P, or permute K. So you do NK, and then you put a little P there, and you insert it like so, so it becomes NPK. And that means N permute K. And it means the exact same thing we've been asking all along, which is how many different ways can you put N objects into K holes, or how many different ways can you put K objects into N holes. Same thing. It doesn't matter which way around you do it. Now, what if instead you wanted to get the number of combinations instead of permutations? Well, you just get this, and then you add on a simple term. You add on the term k factorial. So you just divide here by k factorial, like so. I'm just going to add that on. K factorial, nice and big. This is a good size. No, this size. No, this size. Perfect. So n factorial divided by n minus k factorial, and this thing here is equal to what we do. We do it like this. You have a bracket, kind of like, and you do a bracket, and you do another bracket, and in the middle, it's kind of like you're doing a fraction in the middle of two brackets, except you don't have the underline. You put n on the top, like so, and you put k on the bottom. And this is pronounced n choose k. So this is n permute k, and this here is n choose k. So the amount of different ways you can put n objects into k holes, or k objects into n holes, when you're talking about combinations, is n choose k amount. Is the amount n choose k. And so that has been a review of combinatorics. I will now use this, all that I have taught you, in two ways. I will respond to a video, a question posed by Singing Banana, a YouTuber. He's a mathematician. He's also known as James Grime. He does some videos on the Numberphile channel, but he also has his own channel called Singing Banana. I guess just that's because he signed up to YouTube originally with not knowing what he was going to do with the channel. I'm going to respond to his video, and then I'm going to pose a question to him, and perhaps he can then relay that to his audience, and I'm going to pose it to you guys. It is a question I have already solved, but I want to see if you guys can figure out how to solve it. So, my name is James Ryan, and I have been your host. Believe it or not, I'm actually editing this video, so yeah, I'm going to have to edit a bit. Okay, see you guys later. Bye!